to point out a few things about heat transfer. In any heat transfer, you have a system and the surroundings. The system is the chemical change or the physical change of interest. If we're dealing with a physical change like evaporation or condensation, well, the energy is being used to change the intermolecular forces. In a chemical change, the energy is being used to change the intramolecular forces, the covalent or the ionic bonds. We can't usually measure chemical changes directly, but what we can measure is the impact on the surroundings, the temperature of the surroundings. And the surroundings is usually water, or maybe it's air. And we can measure the starting temperature of the surroundings before a reaction and then the temperature after a reaction. And either the temperature of the surroundings went up or it went down. Well, if the temperature of the surroundings went up, that means it absorbed heat. Where did it come from? The system. So we have delta H and Q. Delta H is the system. Q is always the surroundings, and they work together. So if we have heat going from the system to the surroundings, that's an exothermic reaction. Delta H will have a negative value, Q will have a positive value. But the total value of delta H, the amount of energy given up, is the amount of energy that the surroundings accept. But one is positive, one is negative. All the positive means is that energy was absorbed. What the negative means is energy was given away. If we have an endothermic reaction, well, heat's going from the surroundings to the system, this direction. So the energy value for Q, the surroundings, will be a negative value of energy, and delta H will be a positive value. I also wanted to point out the difference between molar enthalpy and total enthalpy. So for molar enthalpy, here are some examples. Delta H of solution, if something's dissolving, delta H of combustion, delta H of vaporization. Whenever you see delta H in some kind of designation of what's going on, this always means the molar enthalpy, the specific amount of energy per 1 mole. If you just see delta H, well, this isn't necessarily for 1 mole. It's dependent on how much substance is involved in a particular scenario. And you can usually calculate it because you're told in one way or another either a certain amount of mass, and you can use molar mass to find moles, or you are just told how many moles are involved. Now, another thing I wanted to point out, again, delta H is equal to plus or minus Q. So again, which one of these will be positive and which will be negative? It depends on whether it's exothermic or endothermic. When we talk about endothermic or exothermic, it's always in terms of the system. We're always talking about what's happening to delta H. So you need to make sure to use your units properly. So Q is always the energy of the surroundings, and it could have a negative value or it could have a positive value. You think about whether it's going to be negative or positive based on the information you're given, or if you're given M, C, and delta T and you calculate Q, well, right there, Q will either end up being negative or positive depending on the delta T value. If T2 minus T1 is a negative value, or if T2 minus T1 is a positive value. All of your units have to agree with each other. Mass is in grams. Specific heat capacity is joules for every gram of the substance raised 1 degree Celsius. Delta T, your T2 minus T1, is also degrees Celsius.